we defined sine, cosine, tangent, etc. last chapter. In this chapter, we're going to talk about graphing these functions. So in section 3.1, we're going to be talking about just some kind of fundamental facts or descriptors about these sine and cosine functions, as well as a little bit of vocabulary that we can use to describe attributes for them. And then we'll talk about how to go from a graph to an equation, or how to go from maybe just some information about the attributes to an equation. But before we can do any of that, we just kind of need to do a little bit of fundamental information dump. Hold on to your calculators about these sine and cosine functions. So let's talk first about the sine function. So if we talk about the family of all sine functions, the parent function would be y equals sine x. So let's just take a look at the graph of that. And to graph this, I'm just going to use my graphing calculator. So the mode I'm going to use is I'm going to use my calculator in radian mode. And I'm going to go to y equals, and I'm going to graph sine of x. And then to look at the graph, I'm going to do zoom trig. So I get this repeating graph, right? So when we look at a function like this that repeats over and over again like this, I'm going to refer to this as a wave, is the way I'm going to describe this graph. So I call this like a sine wave. Kind of looks like a wave on the ocean, right, where you have crests and troughs. Okay. So the domain for something like this, if I look at the graph, I don't see any holes in my graph or anything. So it appears that my domain is going to just be all real numbers. And that makes sense because one of the big takeaways from last chapter, when we came up with the point definition for sine and cosine, was that now we can do sine and cosine on an angle of any size, right? Positive angles, negative angles, as big as you want, as small as you want. I just spin around the unit, around the unit circle, and I can find the value of sine or cosine for that, right? The range, though, definitely does not look like all real numbers to me. Because the y values all seem to be sandwiched between -1 and +1. So we talked about symmetry in chapter 1. If I look at this graph, what kind of symmetry do you guys see here? So this has the 180-degree rotational symmetry, right? So if I take half the graph, I reflect it across the x and then across the y, or across the y then the x, it would lie on top of each other. We refer to that sort of situation as an odd function. So I'm going to use that same vocabulary here. Again, if I look here, I see no discontinuity, right? There's no vertical asymptote. There's no jump discontinuity. There's no removal discontinuity. So I'm just going to say that this is everywhere continuous. And then I'm going to list 3 or 4 other attributes. We'll define what we mean by these in just a moment. So the amplitude is 1, the midline is y equals 0, the period is 2 pi, and the frequency is 1 over 2 pi. Let's just define what we mean by these 4 things, because these are all potentially new vocabulary. So the amplitude is going to be half of the total height of the wave. Or algebraically, the amplitude is y max minus y min divided by 2. Correct. So you're talking about like the total distance. So you're looking from the lowest spot up to the highest spot, half of that distance.
So on the calculator right now,
The lowest spot is at
from 0, but it's not.
correct. The next one is the midline. This is the average value of the wave. And there's that. So the other way of thinking about it is it basically just divides the graph in half horizontally. So if I look at y equals 0, it looks like there's an equal amount of the graph above and below that line. Everybody's okay with that idea as like a visual descriptor? So algebraically speaking, the midline is going to be y max plus y min divided by 2. For the period, it's the length of one full cycle. So if I look at my graph, let's maybe just pick an arbitrary point to kind of start at. Seems natural to use the origin. So if I do that, my graph goes and does an up part, it does a down part, and then when I'm back to the x-axis, I'd start another up part again. So really, this is like one non-repeating period of my graph, right? So the period is just the distance along the x-axis. So from basically this point to this point is 2 pi. If I looked at my window here, my window is going from negative 6 point yada yada to positive 6 point yada yada. This 6 point yada yada is not just like some arbitrary number, that's negative 2 pi or positive 2 pi. And the x scale, this 1.57 yada yada yada, is pi over 2. So this is, every tick mark is pi over 2 units on there. So pi over 2, 1 pi, 3 pi over 2, 2 pi. Everybody okay with what we're looking at? So if you looked at your unit circle, the values of sine repeat as you move around the unit circle, right? So once you get to like 45 plus 360, it was the same as 45. That's why you're getting the repeated periodic behavior. And then the frequency. So the frequency is just the number of cycles the wave completes in 1 unit interval. The easier way to remember that is just that the frequency and period are reciprocal. So the frequency is 1 over the period, or the period is 1 over the frequency. That's usually much more practical. Okay. Actually, let's go and have the same discussion about cosine this time. So I'm just going to do, right next to all of this, I'm just going to write in red cosine. So you can write it in a different column, or you can write it right next to it. It doesn't bother me, whatever you want to do. This is the way I'm going to do it because it's a little bit less writing for me. So let's look at the graph of cosine. So I'll go here and I'll just change this from sine to cosine. What's changed? If just looking at the graph. Yeah, it just looks like it's not starting at 0, 0 anymore, right? Looks like it's been shifted left or right a little bit. Everybody agree with that? This just looks like the same graph as sine. It's just been moved left or right, depending on which way you want to think about it. Okay. Will a translation left or right change the domain? No. So that's still going to be the same. How about, will it change the range? No. Is the symmetry the same? No. Look at the picture. That's symmetric about the y-axis. It's not that 180-degree point symmetry. We had a term for that. We called those even functions when they're symmetric about the y-axis. The continuity, though, is the same. How about the amplitude? Still be 1. How about the midline? Still the same. The period? Still the same. The frequency? Still the same. So the only thing that changed between sine and cosine from these descriptors is the symmetry. So if I take a look at both sine and cosine at the same time, we do that, and I'm going to have the calculator graph sine using the thick line rather than the standard line so we can tell which one is which. To me, if I look at the graph of cosine, that's the thin line, it looks the same as the graph of sine, but I've just shifted it left here. Everybody agree with that? How much left does it look like? Looks like 1 tick mark on my axis. You guys agree with that? Do you remember how much the tick marks were? They were pi over 2. So the scale, the x scale, tells me how far that was. 1.57 yada 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 is pi over 2. If you don't believe me, there you go. So, okay, come on here. So if I observe that cosine looks like the same graph as sine, just that it's been shifted to the left, pi over 2, I know then I can say cosine is equal to sine plus, or sine x plus pi over 2. Anjali? Of course. Pretty neat, right? So we know now quite a bit about the parent function. What if I want to talk about like any sine or cosine function? That is the word sinusoid. A Sinusaurus rex. Hi, Maya. Thanks. Sydney. That's for you. You in trouble? Oh, okay. If I look at these two equations here, what does this look like? Yeah, these are just the transformation equations applied to the specific sine or cosine function, right? The same thing that we're talking about in chapter 1. Does that ring a bell now that we mentioned that? It's like, oh yeah. Oh yeah. So when we say these A, C, H, and K, those values are real numbers, and obviously A and C are non-zero. That's the symbol for the real numbers. That double-lined R there. So, if I want to talk about these transformational functions, and maybe I want to talk about the same descriptors I talked about before. So for sine and cosine, the domain was the same, right? It was all real numbers for both situations. If I shift my graph left or right or up or down, is that going to change the domain? If it was all real numbers before, if I shift it left, right, up, or down, is that going to change it? No. What if I reflect it across an x or y axis? Would that change it? No. What if I stretched it or shrinked it either vertically or horizontally? No. So guess what? That's a good one. The domain is going to stay the same. He did get me. He asked a stupid question, expect a stupid answer, right? All right. Will the range change? Definitely would, right? If I have a vertical stretch, the range would change. Or if I had a shift up or down, the range would change. Very good. So remember, our transformation map is AY plus K. So the same thing is going to be here for the range. So I'm going to have absolute value of A times 1 plus K, except it, I guess, oops, like that. Because the first value is negative 1, right? Negative 1 times the absolute value of A plus K. And then positive 1 times the absolute value of A plus K. Everybody okay with that? Again, basically just a result of our transformation map. Amplitude. Will amplitude change? Yes. What's going to change it? Not the horizontal stretch. Vertical stretch. What controls our vertical stretch? A. Will the midline change? Yes. What's going to change the midline? Not a horizontal stretch or shrink. Not a shift left or right. Shift up or down will, though. Will the period change? Yes. What's going to affect the period? The horizontal stretch or shrink. Sometimes there's just so many letters, it's easy to say the wrong one. So the period is going to be multiplied by whatever that factor C is. And obviously then the frequency, since it's the reciprocal, it's going to be. So this is some important stuff. This is going to be the kind of key information that we're going to go back to time and time again in this first section in order to do the homeworks. So I want you to, in these examples, to describe the transformation and then list the domain, the range, the amplitude, the midline, the period, and the frequency. So we'll do a couple of examples here just to kind of play with this stuff a little bit. Sam, what's up? Yeah, no problem. So let's first start by writing down our values for A, C, H, and K. What's my value for A here? -4. What's my value for C? 1/2. What's my value for H? 0, and my value for K. So to describe my transformation, I'm just going to write my 1, 2, 3, 4, 5, 6. So the 1 and 2 have to do with the C's. Since C is positive, there's no reflection. But since the absolute value of C is less than 1, I'm going to have a horizontal shrink. Then I'm going to look at my A's. Since my A is negative, I'm going to have a reflection across the x-axis. And since the absolute value of A is greater than 1, I'm going to have a vertical stretch. Since H is 0, there's no shift left or right. Since K is positive, it's going to be up 1 unit. Let's just take a look at the graph here to kind of confirm that. So we'll graph sine first, and then our new friend here, 2x plus 1. And I'm going to graph this new one with the heavy line there. So here's the graph of sine. Here's the graph of our transformation. So if I look, definitely see that it's have that vertical stretch going on, right? It's gotten tall and skinny. It's also been compressed horizontally because I have more peaks and valleys than I did originally. Everybody see that? That's the horizontal shrink, yep. If I look, there's more above the x-axis than there was below the y or below the x-axis. That's the vertical shift. That's the translating it up 1 unit. And if I look, instead of starting above the x-axis, we're starting below the x-axis. That's the reflection. Is everybody okay with what we're seeing? Okay. So to do the second part then, what's the domain going to be? Yeah, it's still all real numbers. The domain and range for all sine and cosine functions is going to be all real numbers. Yes, of course. Abby, right? Okay. Just practicing names. Yours isn't one I knew before the start of the year, so I need to practice it more. It's not your fault I didn't know it. I just never met you. Bye. All right. Range. So we use this. So in our case, k was 1, and our absolute value of a is 4. So that's -3 to +5. Is everybody okay with how I did that? Okay. How about the amplitude? That's the absolute value of a, so that's just 4. The period, what's that going to be? 2 pi times the absolute value of c. The absolute value of c was 1/2, so it's just pi. Let's kind of confirm that. So I have my down part, my up part, and that ends here at the tick mark for pi. So I do have like 1 up and down inside of pi, every pi units. So then I have another up and down, another up and down, another up and down. That looks right to me. And my frequency then is the reciprocal of the period, so 1/pi. Oh, the midline! We forgot to write that one down. What is the midline? So y equals 1. Yep. Are we happy with that? Should we do one more? Let's do one more just to be safe. Sound good to you guys? Too bad, that's what I'm doing. Yeah, what's up? So the y coordinate is like the value of the function. So like if I do ask you what's the value of the function when x is 7, I want the y coordinate. So like it's the average y value when I say the average value or the average y coordinate. So you can just take y max plus y min and average those. All right, so let's say we got this sine of 1/2 x minus 3 pi minus 2. What's my value for a? 1. What's my value for c? 2. What's my value for h? Not 3 pi. Why is it 6 pi? Remember, to be able to see the value, stop talking please. Be able to see our value for h, the leading coefficient on x must be 1. So in this case, I had to factor that 1/2 out. And that revealed to me the h was not 3 pi, but rather 6 pi. So be careful on that. That's a place where I've tricked many a student on the first test.
Yeah.
Not cool.
Not cool.
It is tricky. I'm not going to lie. You should never underestimate the sneakiness.
Ooh.
Yeah. All right. So my 1, 2, 3, 4, 5, 6. Since the C is positive, nothing happens there. Since the absolute value C is greater than 1, I have a horizontal stretch. Since A is 1, nothing happens there. Since the H is positive, we're going to go right that much. And since the K is negative, we're going to go down that much. Everybody okay with that idea? Okay. So what's the domain? Good job. That was the dunker. What's the range? Hi. I do not. Nope. Hey, you guys are being more of a disruption than he is right now. He asked me one question.
I took my calculator.
I have it, and it can't be done.
He tried to flex on me.
Yeah. Yes. All right. Amplitude. What's the amplitude here? Good. Thank you. What's the midline? Let's try to do them in order this time, dummy. You got to say y equals -2. It's an equation for a line, so it needs to start y equals. If you write just -2, I'm going to mark you down on it. Just to be clear. What is the period going to be? Times 2 pi, which gives us 4 pi. And the frequency? 1/4 pi. Any questions on how we filled the rest of those in? How'd I get what? 2 pi times C, or absolute value C, I should say. All right. Let's now take an example of doing the reverse. What if I give you a graph and ask you to come up with an equation? Please don't. Sorry, guys. That's definitely an expectation for this course. Oh, shoot. Never mind. So let's look at this one first. Stretch that out so we can see it. All right, so we want to be able to write an equation of the form that looks like this. I want to be able to figure out my values for A, C, H, and K from looking at this picture. All right. So help me out. What can I figure out? Well, okay. Which letter do you want to work on first? K. All right, we can do K first. So if I look back to the 4 characteristics, I have amplitude, midline, frequency, and period. That was the other one. The one that involves k is the midline. So I know the midline is y equals k. What is the midline in this picture? Y equals 2. That's the midline, is it not? Divides the graph in half.
I was straight up with you. Dividing it by 2.
So the midline is 0, right? Alternatively, you could take the y max, which is something comma 2, plus the y min, which is something comma negative 2, and then divide that by 2. 2 plus negative 2 divided by 2 is still 0, though. That's fine. You could also think about it that way. Everybody happy with the k? All right, what do you want to find out next? C, okay. I know that the period is related to C, and that the period is 2 pi times the absolute value of C. So I need to figure out what the period is in this graph. So how long does it take to make a full up and down cycle for this graph? So we started here, and then we did all the way to here is the full up and down. Does everybody agree with that? So if I look at the label, this is negative 2 pi is here, and positive 2 pi is here. So the period is 4 pi. So what that tells me is 2 is equal to the absolute value of C. So C equals 2 or negative 2. Everybody okay? We'll wait until figuring out which one we want to use there for a moment. Okay? What do we still have to figure out? H and A, right? Which one should we do next? Nope. Let's do A next. I know the amplitude is equal to, well, the reason I don't want to do H yet is if I think about those 4 things, do any of them involve H? No, that's why I don't want to do H next. Right? So amplitude, midline, period, frequency, none of them involve H. So that's why I skipped H. You might as well take H out of the equation. Unfortunately, that doesn't work. What is the amplitude here? So if I go from max, if I go from max to min, that's 4 total units, right? And divide that by 2, I get 2. So A is positive 2 or A is negative 2. Everybody okay with that? All right. Now, what I'm going to do is I'm going to figure out both the sign on A and C as well as the value for H. How I'm going to do that is I'm just going to look at my parent function, in this case, the graph of sine of x. Okay with that plan? So this is the graph of sine of x, just from negative pi to positive pi. That's one cycle there in the middle. Everybody okay? Does it look like there's a reflection going on? Yes. And the reason I can tell there looks like a reflection is because this half is going up, but that half is going down. Everybody agree with that? Okay. Do I have a reflection across the x-axis or y-axis? You're wrong. It's a trick question. It could be either one, right? Is it both? No, it's one or the other. Does it matter which one you pick? No, not really. Which one would I pick? A. I would pick the reflection across the x-axis, so I'm going to pick A to be negative.
So I think I'm right.
In that regard, I'm going to pick C to be positive then, or that forces C to be positive. Is everybody okay with that reasoning? Could I have picked it the opposite? Yes, I could have made C negative and A positive, and that's also going to give me a correct answer, potentially. I have to do some other stuff to account for things there, but there's often going to be multiple correct versions of an answer you could give in this sort of situation. In my opinion, it's almost always easiest to pick A to be positive. Or I'm sorry, A to be the negative one and C to be positive. Excuse me. All right. We still have to figure out H, though. We've now solidified A and C. We went from infinitely many choices down to 2 choices for those. And then we made our choices. So if I look at H, it is 0. Miguel, why do you say that it was 0? Yeah, so it looks like each of them is the same, has the same midline here, right? They both intersect at 0, 0, which is on the midline, which tells me that there's no reflection, or there's no shift going on left or right. Is that okay with you guys? So from here, I can say H is 0. So if I put this all together, I can say negative 2 sine of 1/2 x, and I'm done. I think I stole another graph there. Let's grab you. Yeah, it's just another graph. It's just a little graph, that's all it is. Okay. I liked the order that we did these in. Last time, I think, is an effective order in determining our values for A, H, and K. Or A, C, H, and K, excuse me, forgot to say C. Okay. Which one did we want to find first, then? We did find K first. Let's do that again. What do we have to look at to find K? We have to look at the midline. What is the midline in this situation? You guys agree that it's that? I think so too. So that tells me that the K is 1. Is everybody okay with how I did that? If you wanted to check that algebraically, what do? Yeah, it's y max minus y min divided by 2. You subtract, but since it's 0, it didn't matter. Everybody happy here? Okay. Next, what did we look at? The period. Finding C. What's the period in this case? So if I start from minimum and get back to minimum, that is 1 period. You guys agree with that? Or if you are more comfortable, you could start at the midline, do an up and a down and end back at the midline. I agree that that distance is 1 pi. So C equals 1/2 or negative 1/2. Everybody agree with that? Okay. Next, let's find A. To find A, we need to look at the amplitude. What is the amplitude in this situation? So if I go from min to max and divide by 2, I get 1. So far, so good? Okay. Now what we're going to do is we're going to draw in our parent function and use that to determine whether we have or whether the a's or c should be negative, and then the value for h. So I'm just going to sketch in my parent function here. And I think it might make it easier if I draw in the midline here for everybody to kind of see. So this point is corresponding to the origin on my parent function. Does everybody kind of see that? That they're both points that cross the midline? And I chose to use that one because it's, I don't know, there's no good reason. You could have picked any of them. But I try to pick them close to 0, to the origin as I can. That usually makes life easier. So I went left this much and then up that much to get to that, to do the translation. Everybody agree with that? Good. So the up 1 we know because it's k. If I read this graph, this spot here is pi over 2. So that looks like it's going to be pi over 4. Looks like half as much. Of course. So I'm going to say h is pi over 4. Everybody okay there? All right. Now let's decide if there's a reflection going on. So I'm comparing like this part of my transformed function to this part. There is no reflection going on there. Everybody agree with that? So I would say y equals sine of 2 x minus pi over 4 plus 1. So we said positive, positive. Now, if I had chosen to, say, use this point as my transform point, I would have a reflection. Well, let's just examine. So again, I'm comparing the part that's highlighted in purple with this part. So the blue part and the green part should match up, but they're going opposite ways, right? The blue part starts above the midline and then goes under the midline. The yellow part, or the green part, starts under the midline and then goes above. So there would be a reflection if we chose to do a translation to the right, which would be fine. That's still an acceptable answer. So I could have said, alternatively, or negative sine of 2 times x plus pi over 4 plus 1. Or you could have made it negative 2 with the sign positive out front. That would be a correct answer. None of these are the one that I would have done. There's a yet easier way to have thought about this. Are you ready to hear it? So cosine is a sinusoid also. This particular problem is much easier if I'm using a cosine function. Let me illustrate why. So I'm going to scroll back up to the graph here to do this. I'm going to erase all these horrific marks I've drawn all over this. And I'm going to sketch in the graph of the cosine function. So what I notice is that both the maximums are on the y-axis. That just tells me h is 0. So everything else would remain the same, and say y equals cosine of 2x plus 1. And just be done. So the big takeaway here for us how to choose when to use cosine versus sine. So if the min or the max is on the y-axis, I'd use cosine. Otherwise, I'd probably just use sine. Okay? That's me personally. Technically speaking, if I wanted to use, guaranteed to use sine, if the midline, the point that passes the midline is on the y-axis, I definitely want to use sine. Otherwise, use cosine. You could think about it that way as well. Or it could be, if the min or max is on the y-axis, use cosine. If the point that crosses the midline is on the y-axis, use sine. Otherwise, it doesn't matter. You can think about it that way as well. You're going to have a translation either way, horizontally. Okay with that idea, Megan?
So with reflections, what does it do with both axes and the y-axis?
Well, that doesn't, I mean, it tells you that there's no reflection. If you had a max on the y-axis and a min, you know, like if for the transform function, the minimum was on the y-axis because cosine the max is on the y, that would just tell me that the a is negative, or c. Actually, I take that back. C can't be negative. C wouldn't be negative for cosine. Because, yeah, negative cosine is just equal to cosine. Because it's an even function. Right? Remember, and if cosine is even, that tells me that's true. So I wouldn't ever see a reflection across the y-axis for cosine. And similarly, I remember for odds, this is true. Since sine, we said, was an odd function, I could think of any reflection across the y-axis as just a reflection across the x-axis. So you could, it doesn't matter whether you make the a negative or the c negative, just one or the other would have to be. That's kind of neat, right? Let's stop here.